thanks for joining this session here in the room and also online, certainly. So Frank and I like to showcase you today how a data scientist can collaborate even better with a CAP developer building a CAP application, leveraging some of the HANA machine learning capabilities. So this is about data science utilizing the HANA machine learning capabilities. We want to build an app, which you may have kind of seen if you watched the TechEd keynote last year, about fuel stations and forecasting gas prices. That's kind of the scenario we have been using for this session. We also have a Git repo and a blog post about this session, so you basically can go off after the session and maybe rebuild this on your own. Okay, and with that, let's kick it off. Oops. Back here. Non-Apple user. Oops. This is something we wanted to avoid. That's what happens. Okay. All right. So for those who are not too familiar with the HANA capabilities, HANA Cloud is available certainly as you build your CAP applications on BTP. And HANA has these extended multi-model, smart multi-model capabilities, and different machine learning libraries are part of that asset. There's an automated predictive library and an expert library called the predictive analysis library, which both provide algorithm for the classic scenarios like classification, regression, time series forecasting, and others. So we're not talking about deep learning anything. We're talking about classic machine learning scenarios, maybe the bread and butter scenarios you may also need for your business application. For data scientists, we provide beyond the developer interfaces in SQL, we provide interfaces in R and Python. And that's basically also the role we want to see here today. Data scientists working in Business Application Studio with a Python environment, generating some code, generating some CAP artifacts, and then Frank playing the role of the CAP developer, taking that and embedding this into the application. In our latest release from June 2.17 of this Python machine learning client, we've actually added these additional CAP generation capabilities, which we want to showcase today. For those who are interested in HANA Cloud Machine Learning, every quarter there's new features. Over the course of the last year, there were over 40 new algorithms and algorithm enhancements, including an AutoML framework. So I think it's always worth to stop by and see what we're doing in HANA ML. And as we see now the two personas and roles working together, the data scientists building out the machine learning scenario, so taking the business problem, taking the data, analyzing the data. How should I now approach the scenario? Which algorithm to use? What's the best configuration? What's the best parameters? What's the best input data sets? Then, typically a tedious effort, the data scientist at some point is ready to go. Well, this is, please put this in your applications. That's basically the handshake we have built and thought of, generating the artifacts, CDS artifacts, SQL artifacts, and embedding them in a fast-forward way into the CAP application. So that's what we're going to see. So now let's start with what the data scientist would basically do. So we will see that. Now I need my glasses, sorry. Okay, there's the package HANA ML, and that's basically our Python machine learning client. Python package wrapping all the algorithms which are available in HANA Cloud, and those can be then used from the Python side as if somebody would using scikit-learn or any other open source package. Live connecting against my HANA Cloud instance. Connected. as we need some SQL code, we will be using SQL code tracing. Sure. Okay, now it's executed. And what we'll do now, explore a little bit the data we are working with. All the data is preloaded into the HANA Cloud instance for the purpose of speeding up the demo here. So we have a gas station data set with the gas station names and streets and locations. And we're basically building a HANA data frame. HANA data frame is basically a SQL statement against some data within the HANA instance. We're using here now a method, the count method against the data frame, identifying, okay, we have actually 16 service stations in 5,000 meter range around the SAP headquarters. So we're using a spatial function. And just to illustrate what's happening behind the scenes, the select statement, as you can see in Python, the HANA data frame is simply a select statement against the HANA Cloud instance. So that's a special construct. And for visualizing now the gas stations here in Germany, around 16,000, which are from the demo data set called Tankerkönig. We're basically now collecting that data over again into our Python environment to visualize that, just simply here to make this demo a little bit more interesting for you on a map. So, and here we see the red dots, which are the 16 stations here near the SAP headquarters. So this data set called Tankerkönig, there everybody can download the data for any of the 16,000 stations. For many years, we have about 6 months of data uploaded here into a training data set for 5.5 months and a test data set, which is basically in order to test our forecasting model and visualize the forecast in the end. But the data set is basically a timestamp, the station ID, and then the fuel price. And there's a fuel price change for each of the stations. We have 15 stations. And for this 5.5 months, on average, we could say, on average for each station, there are 3,500 price changes per fuel station. So multiple times a day. I guess some of you have experienced that. The prices change here for the E5 fuel price. If we visualize that here using some sampling, the trained data set has about 50,000 fuel price points. We're using some sampling here to visualize this nicely. Otherwise, the graphic would be too busy. M4 sampling method here we have as part of the Python machine learning client. And just to illustrate another visualization we have here, or the general concept of this Python machine learning client, is we use the HANA data frame as the pointer against the data set. We generate SQL code on the fly, and all the aggregation and calculation happens within the HANA database. And that's kind of how this box and whisker plot here got quickly calculated, also showing a little bit the change of the fuel price and the variability over time. And maybe going up again. Guess which year would this be? Is this year's fuel price data? Any idea? Or could it be last year? I guess it's last year when the war changed the fuel prices here, and also end of June, where we had this 30-cent price drop in Germany with this government sponsoring for the period over the summertime. So this is all data prep and kind of giving you an idea how, in Python you would work with the HANA Cloud instance. Now we want to really go into that data science piece, defining a forecast model. We are using a popular algorithm an automated time series forecasting algorithm called Profit. And there's also a HANA implementation of it, which is called Additive Model Forecast. It basically automates the analysis of change points within the time series, the analysis of different seasonalities. We can add external influences like holidays. That's why we've added a holiday table. And it gives you a very robust forecast in general, because it calculates a forecast between each of the change points. And definitely we've had these change points where the price went up because of the war or went down because of the sponsoring by the government. And what we have additionally done here is we have trained a forecast for each of the fuel stations. So there's some parallelization happening behind the scene, which is called here massive, or in business terms is often also called segmented forecasting, where we're specifying the group ID of the fuel station, where we calculate individual forecast models. And we see that you now look into the table with the forecast model. So for each fuel station, we basically have one model. Then on our additive model forecast object, if we apply the predict method, we can then certainly also predict forward using our test data with the test data frame, and inspect the result set here in tabular format, certainly where we see the what and lower upper kind of confidence bands, which is certainly, if we use some visualization, nicer to interpret. And for those visualizations, we basically capture the actuals and the forecasted value and the timestamps in the respective order in a data frame here. Oops. Okay. Can go back to where I stopped. Here. So the Python machine learning client has this visualization methods here for forecast. Specifically, if we zoom in a little bit, we only see for that whole time period, kind of the last 3 weeks or the last week, which was forecasted. If we zoom a little bit in from the time scale, we would see better. And actually, that intraday periods and price changes are pretty good captured by that model for this distinct fuel station. For another fuel station, it would be different. So every fuel station and its distinct pattern is captured by the approach. So at this point, and the data scientists certainly would do much more to fine-tune the model, it's now the time. What do we do to pass this on to Frank into his intelligent data CAP application? For that, we have, as part of the Python machine learning client, the class of artifact generators. We can generate ABAP classes, we can generate HDI artifacts, and we have improved this now in the current release also to create the CAP CDS definition. So we can specify the namespace, we can specify, do we want the predictions be captured by a table function, so it can be directly called by the Fiori preview. Should the CDS compiler create all the artifacts, etc. So, and the catalog service definition, so that the Fiori previews, the OData interfaces are also directly generated. So that's kind of the enhancements, and we are keen to improve this further, maybe to also generate annotations for Fiori UI elements. Let's see what we can do there. Maybe just one point to mention here, or 2 points. We need to have the final fit or predict methods executed on the Python side at least once. There's also a method here, disable HANA execution. If it's a very hairy runtime scenario, then certainly you can disable the actual execution. Then the code is captured only as generated code and can be passed on. So that's one thing. Fit predict for classification regression. There's also a score method. If you want to use the score method as part of your application, that can also be generated. And then there's the general kind of dimension of using HANA ML within an HDI project in general. The actual algorithms are called from a different schema, from the sys-AFL schema within the HANA database. So you always need the capabilities to call those procedures using synonyms and also the privileged role to be able to execute the pile procedures. But all that is also generated out of the box, which we'll see in a second. And that's then in the end here the magic we call the artifact generator, and give some specifications. What shall be the name of our project? Where do we want to generate to? Which directory? What's the target namespace? And all those options. And we can then basically go into the gen directory and would see what we have generated, starting here, for example, with the service definition. So including the table functions, everything is there. If we go into the DB subfolder, yes, all the CDS artifacts for the CDS compiler to generate, and then there's additional HANA native artifacts, which we basically need in addition. These are the procedures. So we basically have specified what are the parameters the PAL profit algorithm should be called with. What are the bindings, input-output bindings? All that is kind of captured, put into those procedures, and those we certainly then also want to call from the application. And now I would basically share this. We could, in another demo, we have then enabled a specific Git repository where we would sync the artifacts to, but here we basically stay within the same business application studio environment. Now we do the handshake, Frank.
Yeah.
So you go on.
Thank you very much. So my dear fellow data scientists solved the underlying business problem. Now my task is to build an intelligent application on top of it. So let's see if we can do that live. So since the artifacts have been generated but not tested yet, so we want to test those in the database. So what I'm going to do now is I'm generating a database service, meaning an HDI container. So I build a new HDI container and service. I don't like that long name. I give it demo. That's the name of my HDI container. And it will be built now. So what I'm going to do is, I'm waiting until that database service has been created, and I will then deploy those generated artifacts into the database. And since they are all procedures, views, table functions, and so on, I will be able to execute those in the database. And that's what I would like to do to validate if those artifacts are all correct before I include those into my application. So I'm still waiting for the HDI container to be created. So let's, and what I would also do, as Christoph mentioned, we would usually then, he would push those artifacts into a Git. I would then pull them from there for the sake of that demo. We just did it. We're working, since it's a CAP conference, we're working in the Business Application Studio. So I'll copy it over the artifacts in the from the generated folder in the notebook directory to my database folder here in the source, and you can see all this. These are the same artifacts basically, which were created previously. So my HDI container is created. I will then now bind it to my instance. Find an HCI container. Here's the one which I just created. Right. Should be good to deploy those objects into the database, and I can do that now with this icon here with that little rocket. When I press it, it will start now deploying those artifacts into the database. It will not take long, and I will just show the log here. So it's already done. So we should be good to test those artifacts or to see the artifacts in the database. You can go into the container with that little icon here. And now that will open up SQL console inside that HANA database service for that respective HCI container. And here now we should, if everything worked well, we should find those objects. Let's see. You can see some tables. Oh yes, these are the tables which are required for the machine learning algorithms. There's a fit and predict tables. But more importantly, there should also be procedures, since we want to train a model and do some predictions. Let's see if there are also some procedures. Yeah, we can see the procedures here. And I'm interested in the train and predict procedures. So these are the ones which were generated. And let's see if they're really working. This is the train procedure, and let's see when statement. And I can now run. The good part is, as a CAP developer, I'm just validating if the objects are working. There's no need for me to tune the SQL code or to go into details here. I just need to make sure that these procedures are callable in my application, and that's all I need to do. So the training took a little while. So we trained for all these 15 service stations close to the headquarters of SAP. We trained a linear model for those, and we can also now perform predictions. That would be this procedure. You can also look at the create statement. This is the SQL code which has been generated in the background while executing the Python notebook. Also here I can generate the call statement, validate if it's working. Yes, I should see some predictions, similar as you saw it in the notebook. So the group ID, this represents the service station, the timestamp, and then you see here the upper and the lower bound of the predictions. Okay, all good. Last thing which I need to validate is the function. There was also a table function in the code. So let's see if that is there. Okay, table function is also here. And I could now go in and say generate select statement. It's a table function, so you would call it with a select. I could execute, and then again I should see the predictions. Okay, everything seems to work well. Now I can go back to my CAP project, and just maybe one remark. There not only the table functions and procedures have been generated, but there are also some supporting files like the synonyms and the grants file, and they're required in order to get access to the objects, or also to get access to database objects which are not in the same HCI container. So for instance, our training data are in a classical database schema, so we need to set up synonyms and access privileges, and they are also generated. They're generated to some extent. For instance, in the grants file, you will see that this has been all been generated, but in the code which was handed over by Christoph, this field here was left empty. I mean, it was not empty. There was a placeholder in it, and I need to replace that placeholder with the actual user-provided service running in my system. So I need to do some little bit of tweaking and adjusting to the actual environment, but 95% of the code is already there. Okay, that's those pieces. And now, I mean, I'm the only thing which I wanted to do. Okay, database is fine. Let's look at the service. Close the notebook. And the service is here. So there is the CDS. So this should include all the OData endpoints for the catalog service. They were also all generated by the HANA generator. I could manually then enhance this script or this file by adding, for instance, projections to certain entities which I want to include. For instance, there is the point of sales. This reflects the service stations, and I would need to add them manually, of course. But the most important pieces are those two functions here, which will then be reflected on the screen of my applications. And my applications, part of that application is that I will go in and say, okay, now train a model for prices predict, and also do the prediction themselves. So I will create two functions, and those will then be reflected by events on the UI. So there's a prices predict and a model trained function, and the implementations of those functions are here in those handlers. There's an implementation for the prices predict, and this one will then, and here's closing the loop. This will call then this HANA consumption massive additive model predict procedure, which has been generated beforehand. So the only thing which I need to do is write that handler, and this is more or less templated, and add the artifacts which were generated previously in the code here. And this is done on one hand for the predict event, and also for the model train event. And here you can see respectively the other procedure which I tested. This is the training procedure. That's basically all I need to do. I also added a little bit of a UI here on top of a Fiori UI, but that's not part of the story here, so I will leave that out for now. Okay, now let's test this application to see if it's working. So I will. First thing is what I need to do is, I have this CUP conference HDI container. I need to bind my service key to that database service, and then I could start my application locally here. Everything goes well. That's live demo. Yeah. See? Okay. Here you can see then. It's not very good visible, but I hope you can see it. So here you can see all the data endpoints and the Fiori preview. For instance, this is the table function. I can now click on this table function, and I should see the data coming from the predictions of the previously trained model. The only thing which I need to do, I need to select the fields. And then I would see here the service stations and also the upper and lower bound of the predictions. That's good. That's the pre-generated stuff. But here's my application. Let's go in the application. And since we were looking for service station close to the headquarter, let's look for case sensitive. Off. Okay. Go. Okay, there we found one service station, which was in a training model, which has the name Waldorf on it. I mean, there are more. There were 15. There maybe but Waldorf in the name. But now I can click on yeah, and you can see here these are the historic price information which were used for the training. And since I trained the model previously, I can now check if I can also see some predictions. And you see the predictions here. So first part is the historical data, the blue lines, and the red is the respective predictions on top of it. And this basically concludes the test of my application. So what I would now do as an app developer, I would, since I validated it locally, I would now go back to my MTA YAML file and generate the MTA project. And I mean, that runs pretty fast, but I'm not going to do it now because I mean, the deployment of it takes a little while. So once you do that, then you have the MTAR archive generates a new MTAR, and the last step to deploy the application is to deploy that MTAR into a Cloud Foundry space, and then you're good. So that basically concludes the end-to-end scenario which we wanted to show from starting from a data scientist, solving an underlying business problem, handing over those artifacts to an app developer. The app developer takes it, includes it into an application, and there you go. Okay, now
yeah, thanks very much. Maybe you want to just show the block kind of, so as a reference point.
Yep.
Yeah, by Nidhi. So yeah, I guess that's what we wanted to present it. As we said, all the code is available in that Git repo and this block here. And yeah, we're happy now for your feedback, and I hope that resonates with you. Yes.